Hello everyone, this is Professor Ng Ji Kun from Unimas. In the last lecture, we have seen tension failure, compression failure, and balance failure in the beam cross sections. So, in design, we want to reduce the chance that brittle failures will occur. So, both compression failure and balance failure, they are very brittle failures, okay, because the concrete will crush, okay. So in compression failure, the steel will not yield, so there is no distinct point where the beam will indicate the failure of the steel in yielding. Okay. Same as for balance failure also, the steel will yield exactly at the point when the concrete crushes. Okay, so these two types of failure are very brittle. Right? So in design, we want to make sure that the beam will fail in tension failure, okay, where the failure mode is ductile, right? So to reduce the chance that brittle failures will occur, Eurocode 2 requires that beams normally have properties which ensure that tension failures with FST, which is the stress in the steel, is equals to the yield stress of the steel. Okay, so we make sure this would occur in our beam design, right? So based on that, now we want to derive the design formula for single reinforced section. So single reinforced section meaning that we have only tension reinforcement. So here we only refer to positive moment. Okay, so for positive bending moment, then the tension phase is at the bottom of the beam, and then the top part of the beam cross section will be the compression zone. Okay, so in the figure that we're going to see later, okay, then we'll see that the value for lambda is equals to 0.8, okay, for concrete strength of 50 megapascal or less, okay, and then for concrete, which is 50 megapascal onwards to 90 megapascal, then the value for lambda in the figure that we're going to see later will be a function of the concrete characteristic strength. Okay, and then the factor eta, okay, will be defined as given in the following page. So eta is equals to 1 for concrete strength of 50 megapascal or less, right? And then eta is a function of concrete characteristic strength for concrete more than 50 megapascal or less or equal to 90 megapascal. Okay, so these are the illustration that I mentioned just now. So from this diagram here, it's shown that there is a typical cross section with the concrete compression zone. Okay, and then the neutral axis is here. Okay, so you have zero strain here, and then you have maximum concrete strain epsilon Cu3 or epsilon Cu2. Okay, so epsilon Cu3 and epsilon Cu2, if we use Eurocode 2 and for concrete strength of 50 megapascal or less, then this is 0.0035. Okay, you can refer to Eurocode to get this maximum strain in concrete value, right? And then the lambda that is equal to 0.8 for concrete strength of 50 megapascal or less is equals to 0.8. So meaning that this will be equals to 0.8 x. Okay, for concrete of 50 megapascal or less. And then for eta here, for concrete of 50 megapascal or less in characteristic strength, this is 1.0. Okay, And then in the previous lecture, we see that the distribution of the concrete stress is a parabolic profile. Okay, so this is the original profile that we're going to see. Okay, where you have zero stress here. Okay, but in deriving the design equation, we simplify this parabolic area into a rectangular area like this. Okay, so the depth of the stress block here will be 0.8 times x. Okay, so where x is equals to the neutral axis depth measured from the most compressed part of the concrete. Okay, and then in the steel you're going to have strain of the steel epsilon s. Alright, and then you have force in the steel, which is the stress in the steel multiplied by the cross-sectional area of the steel. Okay, so where FYD is the design stress of the steel. Okay, and then AS is the total cross-sectional area of the steel bar that is resisting tension. And then from this concrete compression block here, we are going to get a resultant compression FC. Okay, and then the total force in the steel will be Fs, which is equals to Fyd times AS. Okay, so that will be the cross-section, the strain distribution, and the stress distribution that we're going to use. Okay, for our derivation of the design equations. So in this course, we will be only looking at concrete characteristic strength of 50 megapascal or less. Okay, so to derive the equations for concrete more than 50 megapascal is a bit different, because the value for lambda and also the value for eta, they are different. Okay, so please bear in mind that in this course we will only be looking at the concrete with characteristic strength of 50 megapascal or less. Okay, we will not be looking at any concrete with characteristic strength more than 50 megapascal. Okay, so bear in mind. So in this case, the equation that we derive is only applicable to concrete with characteristic strength of 50 megapascal or less. Okay, so as we have seen in the first chapter, the design strength for the concrete FCD is equals to alpha cc times the characteristic strength FCK divided by the partial safety factor. Okay, so alpha cc is the coefficient taking account of a long-term effects on the compressive strength and of unfavorable effects resulting from the way the load is applied. Okay, so from our Malaysia National Annex, okay, it's recommended that alpha cc is taken as 0.85 for compression in fracture or in bending. Okay, so therefore we substitute alpha cc equals to 0.85, and then the partial safety factor for concrete of 1.5. Then we get FCD equals to 0.567 FCK. Now let us look at a cross section which is rectangular, alright, with only the tensile steel AS cross section. Okay, and then from the previous figure, okay, the maximum strain in the concrete is taken as 0.0035 for concrete characteristic strength of 50 megapascal or less. Okay, and then here we have eta FCD, so eta is 1, FCD is 0.567 FCK, so that is the maximum stress in the rectangular stress block here. Okay, and then just now lambda is 0.8 for characteristic strength of concrete of 50 megapascal or less. So you have 0.8x there, which is the depth of the compression block. Okay, so here we have x, which is the neutral axis depth. So here you have 0 strain, right? And then d is used to denote the effective depth. So remember that this is effective depth of the cross section. Okay, and then b is used to denote the width of the cross section. Okay, so now I want to look at how are we going to get this term here. Okay, so if we take a cross section, let's see it in 3D. Okay, so this is the cross section in 3 dimension. Okay, and then this is the neutral axis, let's say. Okay, so the compression block depth is 0.8x. So the compression block depth is 0.8x here. Okay, and then the stress is 0.567 FCK. Right, so this stress distribution will be distributed across the beam section like this. Okay, so this stress distribution is acting across the compression zone of the concrete. So in this case, we can view it like this. So this is the neutral axis. Okay, so the compression zone is here. Okay, so this is the same beam cross section here that we view in 3D. So meaning that this stress distribution is acting all across this compression zone here. Okay, so the stress multiplied by the width of the section B multiplied by 0.8x will give us a resultant force Fc, okay, or sometimes we call it C, okay, in this case, right? So 0.567 FCK here multiplied by 0.8x here and multiply by B. Okay, we are going to get the volume of this block here. Okay, so the volume of the block will give us the resultant force Fc or C. Okay, so from there we will get 0.4536 FCK Bx. So we take 0.567 FCK multiplied by 0.8x multiplied by B. Okay, then it will be equal to 0.4536 FCK Bx. Okay, and then as for the total force from the steel reinforcement, okay, so if we have two steel reinforcement like this, then the resultant force for the tension will be in the middle of these two reinforcement there. Okay, so this is F, S, or sometimes we use T to denote tension. Okay, so the force in the reinforcing steel Fs is equals to YD, which is the design stress in the reinforcing steel, multiplied by the area of the steel cross section. Yeah? Okay, so if we have two bars, then we just use AS as the cross section of two round bars. Okay, and then previously we have seen that the design stress in the steel is the characteristic strength of the steel divided by partial safety factor gamma S. And for gamma S, in the design situation that we have chosen, that is the persistent situation, gamma S is equals to 1.15. So this is equals to Fyk divided by 1.15, so is 0.87 Fyk. Yeah? Okay, so meaning that Fyd times As will be equals to 0.87 Fyk As. Okay, so that is the basis of all the symbols that we have used in our design calculation. Okay, and then the moment arm Z, okay, is the distance between the two compression and tension. Okay, so this is given as D minus 0.4x. Right. So now if we want the moment of resistance, we can take C times the moment arm Z, or T times the moment arm Z. So here we take C multiplied by moment arm Z, okay, and then if you factorize FCK and BD square, then this term here we can take it as equals to K. Alright. So as expected, M increases with X over D and hence with AS, the cross-sectional area of the steel. Okay, and then Eurocode 2 limits X over D to 0.45 to make sure that the cross-section fails in tension failure. Okay, so if all the beams that we've designed will fail in tension failure, then the steel reinforcement will yield at ultimate limit state. Okay, so if we substitute X over D, which is maximum 0.45, into this equation here, okay, then we'll get the ultimate moment of resistance of a single reinforced section, or the balance moment M balance as M balance equals to 0.167 FCK BD square. Okay, so this 0.167 is called as K balance, right? So if you substitute K equals to 0.167, meaning that you are going to get the maximum moment of resistance for a beam that has only tension reinforcement. Okay, and then the X is equals to 0.45D, or X over D equals to 0.45. Okay, so that will give you the maximum cross-sectional area of AS, okay, that you can use in the design of this cross-section for a singly reinforced section. So now we have already got the term for the compression and also tension. Yeah, okay, so now we want to look at equilibrium of these two forces, because for equilibrium, okay, we need to satisfy total forces equals to 0. Okay, so in this case, the concrete compression must be equals to the steel tension. So we equate the concrete compression, which is 0.4536 FCK Bx, and then the steel tension, which is 0.87 FYK AS. And then if we arrange the term of X over D on the left hand side, then the right hand side will look like this, which is 1.918 FYK over FCK AS over BD. And now we want to look at an example. Okay, so in this example, we're going to determine the limiting value of X over D. Okay, so in this case, we take FYK equals to 500 megapascal. Okay, so meaning that 0.87 FYK is equals to 435 megapascal. Okay, so that gives us the stress in the steel is 0.0022. So normally the steel Young's modulus, we take it as 200 gigapascal. Okay, so now if you look at this strain distribution, okay, then we have two similar triangles. Okay, so in this case, we can take epsilon Cu over X is equals to epsilon S over D minus X. Okay, so we are taking epsilon Cu over X, which is equals to epsilon S over D minus X. So epsilon Cu is 0.0035, okay, over X is equals to epsilon S, which is 0.0022 over D minus X. So that gives us X equals to 0.614 D. Okay, so therefore, if X over D does not exceed 0.614, the tension reinforcement of Fyk equals to 500 megapascal in characteristic strength will reach the design strength of 0.87 Fyk at the ultimate limit state. So Euro Code 2 limits the X over D ratio to 0.45 so that the steel reinforcement used at ultimate limit state. So what it means here is that when you have 0.0035 here, and then the strain in the steel is 0.0022, then the neutral axis depth X is equals to 0.614 D. Okay, but in Eurocode, okay, X maximum is 0.45 D. So if when X is equals to 0.45 D, the strain epsilon S is definitely greater than 0.0022. Okay, when the strain in the steel, as we have seen in the stress strength curve for steel, okay, where 0.0022 is here. So if the strain is greater than 0.0022, then the stress in the steel will be the design stress FYD. So that's what it means that by the steel reinforcement will reach the design strength of FYD or 0.87 FYK. Now if we use the steel tension to calculate the moment of resistance, then it will be Fs multiplied by Z, okay, or T multiplied by Z. And then if you move As to the other side of the equation, you move As to the left hand side and move M to the right hand side, okay, then we are going to get this equation here. So this equation 3.7 here is actually the design formula for tension reinforcement in singly reinforced section. Okay, So this equation can be used to design the area of tension reinforcement in a singly reinforced concrete section to resist an ultimate moment M. Okay. So however, the moment arm Z in equation 3.7 needs to be determined before the area of tension reinforcement AS can be calculated. So now we want to derive the equation, okay, for the design. Okay. So from equation 3.5, okay, we can arrange the terms to get x equals to d minus z over 0.4. Okay, so if we substitute x equals to d minus z over 0.4 here and here, okay, then we are going to get this equation here. So if you expand this equation, okay, then we will get a quadratic equation like this. Solving for that quadratic equation, we get z over d equals to 0.5 plus square root of 0.25 minus k over 1.134. Okay, and then we just take d to the other side of the equation, or to the right hand side of the equation. Then we get z equals to d times in bracket 0.5 plus square root of 0.25 minus k over 1.134, then cross bracket. Okay, so this equation 3.10 here is also a design equation that we use in the design of the reinforcement for singly reinforced section. Okay, so here equation 3.7 and 3.10 are used in the design of the area of tension reinforcement for a single reinforced concrete beam section with K less than K balance. So this is a very important criteria. Okay, when K is equals to K balance, then X equals to 0.45 D. So that is the maximum neutral axis depth that is allowed in Eurocode 2 design. Okay. If K is greater than K balance, then compression reinforcement is required, which will be discussed in the next section. Okay, so bear in mind that equation 3.7 and equation 3.10 can only be used to design beams with K value less than K balance. Okay, and then to provide area of tension reinforcement, the reinforcement should be within the minimum area and the maximum area. So you refer to Eurocode 2 section 9.2.1.1. Okay, then you will be given an equation of AS minimum, which is equals to the term here where you need to find FCTM. Okay, so FCTM is a concrete tensile strength that can be obtained from table 3.1 of Eurocode 2. Okay, and then BT is the width of the tension zone, of which for a T-beam with the flange in compression, only the width of the web is taken into account in calculating the value of BT. Okay, and then AC is the cross-sectional area of the concrete beam, and then H is equals to the total height of the beam. Okay, so just now we have a cross-section, okay, with H is the total height of the beam. And then remember that we have effective depth D and also width B. Okay, so B times H is the total cross-sectional area of the concrete beam, AC, right? And then X maximum is 4% of the cross-sectional area of the concrete, so it's 0.04 AC, which is 0.04 BH, right? Now let us look at one design example where we design the area of tension reinforcement for this beam. So the design ultimate moment MED for a rectangular beam of width B equals to 250 mm and effective depth D equals to 650 mm is 300 kilonewton meter. Okay, the concrete characteristic strength is 35 megapascal and the steel characteristic strength is 500 megapascal, and then the total beam height is 700 mm. So in design, normally we equate MED to MRD. Okay, the requirement is that MRD should be at least equal to MED. Okay, so for simplification's sake, we just equate MED to MRD in our design. So first of all, let's look at how we start with the design calculation. So first we need to check whether x over d is greater than 0.45 or not. Okay, so we don't directly check x over d, but we check the value of k. Okay, if k is less than 0.167, okay, then meaning that x over d is less than 0.45. Okay, so this is what we have calculated here. So k is smaller than k balance of 0.167. So we can conclude that x over d is less than 0.45. So this is to check and make sure that the beam is tension failure at ultimate limit state, or it is under reinforced. Next, we calculate the lever arm Z. So lever arm Z, we use the equation that we have derived before. So we just substitute K into the equation, and then we get lever arm Z is equals to 600 mm. So in this case, by using the equation that we have derived before for the design, then AS required is 1150 millimeter square. So this is the required steel cross-sectional area that we need to put into the beam. Okay, so how do we design with this much of steel? Okay, so we refer to this table A here in your design guidebook. So this table gives us the standard bar size that we use in design of reinforced concrete. Okay, so the standard bar size or the bar diameters are 6 mm, 8 mm, 10 mm, 12 mm, so on and so forth until maximum 40 mm. However, 40 mm bars are seldom used, as well as for 32 mm bars are also seldom used. Okay, so normally we design to these bars only. Alright, and then on this side of the table, it gives you the area of the steel bar with 1 bar, 2 bars until 10 bars. Okay, anything more than 10 bars, you just add up the area. Okay, let's say for 11 bars, you just add 10 bars area to 1 bar area. Okay, so just now our required steel area is 1150 square millimeter. Okay, so we go through this table here. Let's say we decide to use 20 mm bars. So we go from left to right to see where we can get an area that is about 1150 mm. So in this case, it is this 1257 square millimeter. Okay, so this corresponds to 4 bars. Alright, so we specify 4H20 in the design. So we design 4H20, okay, for the beam. Okay, with AS provided, that is 1257 square millimeter of cross-sectional area. Okay, and then for minimum reinforcement, we use the equation that is in the Eurocode. Okay, so from table 3.1 of Eurocode 2, okay, The tensile strength of concrete is 3.2 megapascal. Okay, for FCK equals to 35 megapascal. So you calculate as minimum, okay, based on FCTM equals to 3.2 megapascal, and we get 270 square millimeter. So this is the minimum steel bar area that you need to provide. Okay, and then this value here cannot be less than 0.0013 BD. Yeah? Okay, so 0.0013 times B times D is 211 square millimeter. Okay, so meaning that this 270 square millimeter value is okay. Okay, so this is the minimum steel area. Okay, and then for maximum steel bar area, AS max is 4% of the concrete cross section. So the concrete cross section is 250 by 700 mm. The overall height of the beam is 700 mm. So this is B, this is H. Okay, so we get 7,000 square millimeter. So in this case, the provided steel is more than 270 square millimeter and is less than 7,000 square millimeter. So we say that the design is okay. Okay, that's all for the lecture for this section. Thank you very much for listening.